Welcome students or friends. This is our first class in quantum mechanics. So to go deep in this subject, quantum mechanics, we first know the history. What history? Why quantum mechanics comes forward? Okay, because there was in 19th century there was classical mechanics, magnetism. Physics consisted essentially of classical mechanics, the theory of electromagnetism and thermodynamics, which was satisfied, which was successful. Then why quantum mechanics comes forward? The success of classical mechanics, classical theory of electromagnetism and thermodynamics made people believed what people believed, that the ultimate description of nature had been achieved. Okay, it seemed that the all known physical phenomena, everything could be explained with the frame of classical theory. Okay, then why? Okay, so at the turn of 20th century, however, classical physics was seriously challenged on two major fronts. Now what are those fronts? Here we begins. Okay, what are those fronts? First is relativistic domain. What is the case? Let's see. Einstein's 1905 theory of relativity showed that the validity of Newtonian mechanics ceases at very high speed. Okay, it means when a particle is in very high speed comparable to the speed of light, then what is the concept of giving that particle a force, her acceleration, because it is very high speed, relativistic domain. Okay. Number two is at microscopic domain. As soon as new experimental technique were developed to the point of probing atomic and subatomic structures, it turned out that classical physics fails miserably in providing the proper explanation of several newly discovered phenomena. This means at first classical physics was very much successful, but in these two cases, relativistic domain and microscopic domain, it fails to describe, in this case, to describe the phenomena, to describe the motion. Classical mechanics or electromagnetism, thermodynamics, which I say, fails. The introduction of quantum mechanics was prompted by the failure of classical physics in explaining a number of microphysical phenomena. This was the main reason why quantum theory or later quantum mechanics comes forward. Okay, so first quantum theory comes, then quantum mechanics. So we will go through this arena, how this quantum mechanics comes, the history. Without knowing the history, we can't gain the proper interest in this chapter. Okay, so today we will not just calculate any theoretical or any calculations. We will know just only the theory. We will learn the theory, history, why this quantum mechanics comes forward. This is our main motto. So we get 2 points. Why classical mechanics fails? First we done an experiment and we saw that in this two domain classical mechanics fail. Okay. What are the microphysical phenomena? Like number one, black body radiation. Okay. Number two, photoelectric effect. Number three, atomic stability. Number four, atomic spectroscopy. Okay, these are the microphysical phenomena which can't be described by classical physics. So we are entering into the new arena. Okay, now what was the first step? See, We know this man, this famous man. Who is? This is Planck. Max Planck. Okay. So this he took the first step. First step. What did he done? In 1900, Max Planck introduced the concept of quantum energy. Quantum energy. Okay. He made us believe that energy exchange between an EM wave. Energy exchange between an EM wave of frequency. The frequency of this wave is say nu. Okay. Then the energy exchange of the EM wave occurs only in integer multiple of h nu. Okay. That means, what did it means? That means in integer multiple means in discrete quantized amount, isn't it? If the energy exchange between EM wave is in integer multiple of h nu, that means it is the energy exchange is in discrete quantized amount, isn't it? So Max Planck showed us this. Okay, where h nu equals to energy of a quantum what we called h equals to Planck constant. Planck's constant. We must remember, what are we trying to do? We are entering into the quantum arena from classical arena. Okay. So first step was taken by Mr. Planck, Max Planck, and he observed these things. Then second step. Here comes our godfather. Okay. Our godfather, Einstein. In 1905, Einstein, to understand photoelectric effect, what was his motto? Photoelectric effect. Photoelectric effect. Photoelectric effect, Einstein used Planck's idea. What idea? That when exchange of energy from electromagnetic wave, it is in integer multiple of discrete amount of quantized amount. Okay, which is h nu, multiple of h nu. Light itself made of discrete bits of energy called photons. Same idea he took from Planck's energy of h nu, nu being the frequency of light. Okay, he described the photoelectric effect. We will see later what was the description others. So we first see the steps. How comes from the classical mechanics to this quantized and discrete matter, which will be later called quantum. Now another breakthrough. Yeah, third step was due to Niels Bohr. Right after Rutherford experimental, we all know the Bohr model, Rutherford model. Why there were some difficulties in Rutherford model, then later Bohr's model comes. Right after Rutherford's experimental discovery of atomic nucleus in 1911 and combining Rutherford atomic model, Planck's quantum concept and Einstein photons, Bohr introduced in 1913 his model of hydrogen atom. He argued that atom can be found only in discrete state of energy, and that the interaction of atoms with radiation, that is the emission or absorption. We all know this type of pictures. When a particle from these energy states E2 comes to this energy state E1, then E2 minus E1 equals to h nu. This is a discrete quantum of energy. Okay. discrete amount of h nu, because it results from transition of atoms between its various energy states. Transition of the atoms. Okay, these are the transitions. Okay, so I am again telling what our main motto. Our main motto is to come into the discrete energy states, quantized states, that is quantum. Okay, transition from atom, various discrete energy states. These works provide a satisfactory explanation to several outstanding problems such as atomic stability and atomic spectroscopy. Okay, now let's come. Then in 1923, what Compton done? By scattering X-rays with electron, he confirmed that, let's see, this is the all same things. Everyone is finding the same things, which classical mechanics, classical theory was unable to describe. Okay, that the X-ray photons behave like particle with momenta h nu by c. Now, if quantized energy h nu by h nu and momenta h nu by c, obvious, we can convert momenta to energy, energy to momenta, h nu by c. Nu is the frequency of X-rays. Okay. Next, Broglie, or say de Broglie, introduced in 1923 another powerful new concept that classical physics could not reconcile. What are we understanding? That these are the phenomena which classical physics could not reconcile. It is for classical physics, it is unable to describe the theory or experimental values or anything. He postulates that not only does radiation exhibit particle-like behavior, but conversely, material particles themselves display wave-like behavior. This is a very important point of de Broglie. Again, what the result? Does radiation exhibit particle-like behavior, but conversely, material particle also behave like display wave-like behavior? This series of breakthrough, this series, first Max Planck, then Einstein, then Bohr, then Compton. This series of breakthrough due to Planck, Einstein, Bohr, and Compton gave us theoretical foundation. What we get? What we got? Theoretical foundation. Theoretical foundation as well as experimental. Plus we get experimental confirmation, na? Experimental confirmation here in photoelectric effect, experimental confirmation, then discrete energy transitions in a Bohr's model, plus, and obviously in Compton's, this was the experimental confirmation. For what? For particle aspect of wave. This is a very important point. Okay. Now, what is the summary of till now? The concept that waves exhibit particle like behavior at the microscopic level or scale. Okay, this is the main point. Why quantum theory, quantum mechanics comes forward. This is the history, and after this history, why quantum mechanics comes forward? Because wave exhibit particle-like behavior at the microscopic level, which is undescribable by our classical theory or classical physics. So, at this scale, classical physics, which was so famous, which was so successful, fails not only quantitatively but even qualitatively also. Okay, and obviously conceptual. There was very misconceptions if we try to describe these topics in classical theory. There will be very misconceptions. So conceptually also. So conceptually also classical physics fails. Okay. So this was actually for classical theory, classical mechanics, this was very bad time. Okay, but this was not enough actually. Then Davison and Jalmar, they made an experiment. Okay, they showed that interference pattern and property of waves can be obtained with material particles such as electron. Then Heisenberg and Schrödinger. Okay, first we go through this history, how this quantum, the idea of quantum comes. We see that. Then Davison Jalmar showed experimentally, and then Heisenberg and Schrödinger. To Heisenberg and Schrödinger, what did done? To search for the theoretical foundation of this idea, they tried to found the theoretical foundation of this idea. Okay, because to make people understand, to believe them, why we will adopt this experimental result, what is the description of this result. They tried the theoretical foundation, to search theoretical foundation of this idea. So here a refined arena is almost came, which is quantum mechanics. Which explains the microphysical world. Isn't it so much interesting that Newton, our first godfather, whose theory is getting old for this microphysical world, and new quantum mechanics, quantum theory, quantized, quantum, these words are coming into our front. Okay, it explains the microphysical world. Now, there were two independent formulations of quantum mechanics. The first formulation, called metric mechanics, was developed by Heisenberg to describe atomic structure starting from the observed spectral lines. What are we seeing now? We are seeing independent formulations, two formulations. First was made by Heisenberg. Heisenberg founded his theory on the notion that the only allowed values of energy exchange between microphysical systems are those that are discrete quanta, which we saw earlier. Expressing dynamical quantities such as energy, position, momentum and angular momentum in terms of matrices, he obtained an eigenvalue problem, which we show later, problem that describe the dynamics of microscopic systems. So here the matrix method, mainly Heisenberg came forward with matrix method. Okay, was very successful in accounting for discrete quanta. Successful, it was also successful for discrete quanta. Discrete quanta of light emitted and absorbed by atoms. Okay. Now, instead of matrix eigenvalue problem, and in matrix we will also see the eigenvalue problem. Eigenvalue problem. Okay. Now, instead of this eigenvalue problem, Schrödinger, here we come. The next foundation, the next second formulation was wave mechanics was due to Schrödinger. It is a generalization of the de Broglie postulates. Now, instead of this Heisenberg's matrix method and eigenvalue problem, for generalization the theory, for expanding it everywhere, Schrödinger comes with wave mechanics. Okay, this describes the dynamics of microscopic matter by means of wave equation called Schrödinger equation. This is what? This is a differential equation. We will see what is the equation. This generalizes. This is the main point of view of our quantum mechanics will be. Okay. The solution of this equation yield the energy spectrum and the wave function. This is a differential equation of what? Of a wave. That's why it is a wave equation, na? The solution of this equation yield the energy spectrum and the wave function of the system under consideration. Now, in 1927, Max Born proposed his probabilistic interpretation of wave mechanics. From this wave function and wave differential wave equation, Max Born probabilistic interpretation of wave mechanics. He took the square moduli of the wave function that we will see later. We will see this later when we go through deep in the quantum mechanics. Okay, today we are now just only finding the history why quantum mechanics comes from classical theory. Classical theory failed. And now new microphysical world. They quantum mechanics describe this world well. So wave function that are solutions to the Schrödinger equation and interpreted them as probability densities. What I am circling, this is the main point, this is the main arena of our discussion. Now, combining special relativity and quantum mechanics, Dirac describe what? An equation which describe motion of an electron. Dirac then suggests a more general formulation of quantum mechanics which deals with abstract objects such as Kates. What are Kates? State vectors, bras and operators. Okay, what are they? We will see in later class. We just only rounding with the point of why quantum mechanics comes, the history and why it comes. Okay. This equation, special Dirac, what did he done? He took special relativity and quantum mechanics and make a equation. This equation known as Dirac's equation predicted the existence of an antiparticle. From this equation, he predicted an antiparticle, that is this positron. And what is it? It is similar in properties but opposite in charge. With whom? With electron. This acts as an antiparticle. Okay. So now we are in the middle of microscopic level. Okay, microscopic level. So the summary of this class is, first there was a very well known classical theory. Some they are failed in relativistic domain and macroscopic domain. Then why we will quantum mechanics comes. Then first step Planck's black body radiation. Then second step photoelectric effect of Einstein. Then comes Bohr. Then comes our Compton experiment. Okay. So now we are in Schrödinger equation and in Dirac's equation. Okay. So what is the summary? In summary, quantum mechanics describe the dynamics of matter. Quantum mechanics describe the dynamics of matter in microscopic level. Microscopic level. Here classical theory fails because in microscopic level, where you will find the force, where you will give the force, exert the force, where will be the acceleration or velocity or anything, any properties of that particle, where you will find that, how you will measure that. There is a huge measurement problem, na? There is a huge measurement problem in microscopic level if we done with classical theory. So quantum mechanics describe the dynamics of matter in microscopic level. Fine. For only this we will study this huge quantum mechanics, this huge quantity of books. No. It is vital for understanding the physics of, number 1, solid state. Okay. Number 2, lasers. Number 3, semiconductors. Number 4, superconductor. Wow. Isn't it interesting? 5, plasma. Can classical theory describe these things? Yeah. Physics is same everywhere. Classical physics can describe, but there will be a lots of error. We will even not get the experimental data matched with the theoretical data. Okay, plasma, etc. Okay. In short, what will be a summary? In short, quantum mechanics is founding basis of all modern physics. These are the reasons why we will study the quantum mechanics. For not only that it describes the microscopic level well from classical theory, for not only this, for these reasons, okay, basis of modern physics. Solid state, molecular, we know the names, na? Solid state physics, molecular physics, but we will know in detail about that. That's why you need a new mechanics. What is that? Quantum mechanics, molecular, atomic physics, nuclear physics, particle physics. They are each and every parts of every aspect of physics, and these are so interesting. So we must know the basics. Then we will be interested to know in the deep. No. Optics, even thermodynamics, because the same physics is everywhere. Statistical, etc. Okay. So why So we see that why we will study quantum mechanics, not only for these reasons that in microscopic level classical physics fail, for the all these reasons also. Okay, so this was the summary of today's class. There was no difficult calculations or nothing. We just see the history. We just saw the history why quantum mechanics comes, why in such arena classical physics, thermodynamics, electromagnetism can't give us the fruitful results. Okay, so uh, enough for today. Next class we will continue. Thank you.